Yes, good morning, my dear friends, and welcome to electronics online classes. As usual, you are discussing about the applications of operation amplifier, and already we have completed the linear applications, and you have started about the non-linear applications. And in that non-linear application, in the last class, we have discussed about the how op-amp can be used as a differentiator and integrator. As we know already, the op-amp can be used to concept the linear devices as well as non-linear devices. That is the importance of your operational amplifier. And also, as we know already, why the op-amp is called operational amplifier? Because as we know, it will perform the mathematical operations such as addition, subtraction, and multiplication, differentiation, integration that you have studied in the last classes. But today we discuss another so important concept, and also in general we want in mathematics also in general we want addition, subtraction, multiplication, division and integration, differentiation, and another we want more important thing, that is about we want sometime log of a value or anti-log of a value. If you want to calculate the log value or anti-log value, and how to calculate log and anti-log, that is also possible by using your operational amplifier. It means how your op-amp can be used as a adder, subtractor, differentiator, integrator. In the same way, the op-amp can be used as a logarithmic and anti-logarithmic amplifier. That we will discuss in the today's class. As usual, the lecture number 8. Today we are going for the lecture number 8. We are going for the lecture number 8, and in the previous class we were discussing about the how op-amp can be used as a differentiator and how it can be used as an integrator. And as I said already, these are all called non-linear applications. As we know the meaning of linear, non-linear, nothing but output and input are not direct proportion. The output and input are not direct proportion. And also, as visual, as I said, in op-amp you can externally add the capacitor and diodes. As usually having the resistance is there in the input as well as output. But how you already discussed about differentiator, integrator, if you are connecting the capacitor to the input, your op-amp is used as a differentiator. The same capacitor if you connect in the output, your op-amp is used as an integrator. It means depending on the way you are connecting the capacitor in the input or input output, we are having the different applications of your operational amplifier. And as I said, you know already where you are using the differentiator, integrator circuits. As I said, because your op-amp is analog IC, especially in analog computers, we are using about your differentiator integrated circuits. Also, as I said already, if you are going in your wave shaping circuits, or you are using in your low pass and high pass filters. And as usual, we know about the differentiator, it is a circuit or it is an amplifier. In this differentiator circuit, the output is proportional to the derivative of the input. In differentiation, the output voltage is proportional to the derivative of input voltage, or the output voltage is proportional to the differentiation of the input voltage. That is, you know, already we studied in the last class. That is about differentiator. And the integrator, nothing but, as I said, only you want to change the connection, where you have to connect the capacitor. If you connect the capacitor in the output side, that becomes your integrator. And integrator, nothing but is also circuit. In this circuit, the important thing is about the output voltage is proportional to the integration of the input voltage, or the output voltage is proportional to the integration of the input voltage. That is nothing but your op-amp is used as a differentiator and op-amp is used as a integrator. Now in the today's class we go for how the op-amp can be used as a logarithmic amplifier and how it can be used as a anti-logarithmic amplifier. You have completed nearly, actually I said it is very big topic, and especially you are having nearly about 8 derivation. In that 8 derivation they will ask any one derivation for 5 marks, and it means you have completed the 6th derivation, another 2 derivations are remaining. That is, we will go for today's class how your op-amp can be used as a logarithmic amplifier and how your op-amp can be used as a anti-logarithmic amplifier. And as usual we go for the mathematical proof for that how your op-amp can be used as a logarithmic amplifier or it is used as a anti-logarithmic amplifier, or you can say derive the derivation for op-amp, how your op-amp is used as a logarithmic amplifier or how it is used as a anti-logarithmic amplifier. And before that, what is the necessity of your logarithmic and anti-logarithmic amplifiers, or what are the applications where you are using the logarithmic and anti-logarithmic amplifiers. As usual, we know if you want to draw the frequency response or if you want to find the bandwidth, because you are having bandwidth nothing but range of frequencies, the gain will be constant. It means we are having so much of frequencies. Frequency range is very more. That frequency range is not possible to draw in the normal linear graph. That's why we prefer you take the logarithm scale. You take the logarithm scale, then you can draw the frequency response and you can find the bandwidth. It means whenever you are finding the bandwidth of an amplifier, you are using the concept of logarithmic scale. And as usual in your sensors, if the sensors having the more range of the values, that range can be reduced or that range can be mentioned by using your logarithmic amplifiers. You can use the logarithmic amplifiers or you can use the logarithmic scale. And as usual, another important thing, as I said, the op-amp can be used as a multiplier, it is also used as a divider, or you can multiply the voltages or you can divide the voltage. That is by using your logarithmic and anti-logarithmic amplifiers. You can analog voltage can be multiplied and also analog voltage can be divided by using your logarithmic and anti-logarithmic amplifiers. And also, as usual, you can find the square root by using the logarithmic and anti-logarithmic amplifier. You can find the square root of the any value, any signal. You can find the square root. Also, you can find the RMS value. That everything possible by using your logarithmic and anti-logarithmic amplifier. And I will go for the basic about logarithmic amplifier. We are going for the logarithmic amplifier. And as I said, you people, what is logarithmic amplifier? Once again, it is a type of amplifier. In this amplifier, the output is proportional to the logarithm of the input voltage. Once again, repeat, what is logarithmic amplifier? The logarithmic amplifier, it is a type of amplifier. In this amplifier, the output voltage is proportional to the logarithmic value of the input voltage. Or in simple way, the output voltage is proportional to the log of the input voltage. Especially in logarithmic amplifier, the output voltage is proportional to the, I can write proportional to the of the input voltage. Or you can write the symbolically, the output voltage is proportional to the log of the input. This we can derive here. It means by the definition of your logarithm amplifier, what you can derive here is, what is logarithm amplifier? Nothing but the logarithmic amplifier. It is a type of amplifier. In this amplifier, output voltage is proportional to the log of the input voltage. This is nothing but the importance of your logarithmic amplifier, and they may ask the 5-mark question. Explain how your op-amp can be used as a logarithmic amplifier, or derive the direction for how your op-amp can be used as a logarithmic amplifier. Means first you are the write the definition. The logarithm amplifier, it is a type of amplifier. In this amplifier, the output voltage is proportional to the log of the input voltage. And as usual, we know about the basic concept of your logarithmic by using the rules of logarithmic. That is, one is about log m into n, nothing but log m plus n, log m plus n, and also you can use the log m by n, nothing but log m minus log n, and finally, as we know, log m raised to n, nothing but n log m. These all three rules, formulas can be verified by using your logarithmic and anti-logarithmic. As I said already, by using your logarithmic amplifier, you can multiply the voltages. You can multiply the analog voltages. Also, you can divide the analog voltages, and also is used for find the square root of any number or any voltages. This is about in brief about the logarithm amplifier. Now we go for the circuit diagram and also its explanation and derivation for how your op-amp can be used as a logarithmic amplifier. Especially, as I said, you people in integrator and differentiator you are using a capacitor in the input, or it may be the output. But in logarithmic amplifier you are using a diode, and also some book they are given, they are also using the transistors. But according to your syllabus, they are using the diodes. Can use also transistor. And if you are using the diode in the output side, in the feedback path, that type of amplifier is nothing but the logarithmic amplifier. It means if you are connecting the diode in the output side, that type of op-amp is nothing but the logarithmic amplifier. And the same diode if you connect in the input side, that is nothing but anti-logarithmic amplifier. Only the change is about where you are connecting the diode. If you connect diode in the output side, that is nothing but logarithmic amplifier. The same diode if you want to connect in the input side, that is nothing but anti-logarithmic amplifier. Now we will go for the diagram, then you can understand very easily about the concept. As usual, you are considering the inverting mode. You are considering the inverting mode. As usual, you are considering the inverting mode. Because you are using the op-amp is used as inverting mode, make it non-inverting terminal ground. Make it the non-inverting terminal ground. And as usual, you are using diode. You are using the diode in the feedback path, and you are applying the input to the op-amp by using an RI, the input resistance. You are applying an input signal. As usual, it is similar to this is your VD and this is your ID. This may be IF. This is is your IN, and this is your IB, and this is VA, and as usual you are using an here you can measure the output voltage. This is minus VEE, this is your plus VCC. You are using an plus VCC. Look here, as I said already, only the small change. Everything is similar to the inverting amplifier. Only thing here in inverting amplifier using the feedback resistors in the output side. You are using a resistor here. In case of resistor, you are using the diode. If in case of resistor, which we are using diode in the output or in the feedback path, that type of amplifier is called the logarithmic amplifier. And in this logarithmic amplifier, as usual, you are applying the input to the inverting terminal through the RI and you make it non-magnetic grounded. And here you are using in the output side, you are using a diode in the feedback path, and as usual you are applying the biasing voltages. Because you are using the diode in the feedback path, because you are using the diode in the feedback path means we want how much the current go through the diode. As usual you are studied in the first year, you know, in the basics, the diode equation. What is also called a Shapley equation. Is called Shapley's equation. It is nothing but ID equal to IS e raised to VD by eta into VT, minus 1. This is you started already in the first year. This is the diode equation, is called Shapley equation, and this equation indicates how much the current flow through the diode and what is how much the voltage drop across the diode, and it will give the information about current and voltages. As usual, here ID nothing but diode current, IS nothing but reverse saturation current, and VD nothing but the voltage across the diode, as written here, the voltage of the diode, and this eta nothing but ideality factor, this VT nothing but thermal voltage. And especially for the diodes, actually this e raised to VD and VD is more than 1. That's why you can neglect the 1. We can write ID equal to IS e raised to VD by eta into VD. Because or you can write one step here for any confusion means the e raised to VD n eta is more than 1. That's why you can write ID equal to IS into e raised to VD by NVD. This you are using this diode equation in the empty logarithm as well as in the logarithmic amplifier. As usual, how you have done the differential indicator, you have used that how much the current flow in the capacitor. The same way you have to find out the how much the current flow in the diode. And as usual, you can apply the KCL. Apply KCL to node A. That becomes as usual the IN equal to IB plus IF, and IN as it is as usual, because IB is 0, we because of, as you know already, because of input impedance is infinity, because we are considering the ideal of them, and it becomes In equal to IF. And as usual, In we can write Vi minus VA by RI, and here in case of IF can write here IF is equal to ID, because IF only, but in case of using the diode, that's why IF is equal to ID. Then I how we can write VI minus VA by RI, and here in place of IF can write ID, because IF is equal to ID. Then the VA is 0 because of virtual one concept, as you know already, that becomes VI by RI. And here in case of ID, what you can write? IS into e raised to VD eta into VD. You can write IS e raised to VD NVT, and here because VD nothing but the voltage across the diode, and because it is in the output side, we can write how we can write VD VA minus V0. We can write here VD equal to VA minus V0, and here once again VA 0, you can write VD equal to minus V0. It means in place of VD you can write minus V0. That becomes VI by RI equal to IS into e raised to minus V0 by eta into VD. Then in next step what you will do? Next step you take IS this side, that becomes VI by RI into IS equal to e raised to minus V0 eta into VD. Next step what you have to do? Take log on both sides. Take log on both sides. Then you take log here. Log of VI by RI into IS. This is equal to here log of e raised to minus V0 by NVT. Look here, the important thing is about log m raised to l. It means this should divide here, and as usual log e to the base e is 1. Okay, right? This is right as it is. Log VI by RI IS as it is, and here this will multiply here, that becomes minus V0 by eta into VT, because log to the base is 1. It means we can write log of VI by RI into IS equal to minus V0 by eta into VT. And actually we want V0, this eta into VT will multiply here. You can write V0 equal to minus eta into VT into log of VI by RI into IS. Actually, this eta into VT and RI and IS, they are constant. We can write V naught is directly proportional to the log of V. This is about the important derivation for the logarithmic. As I said, only change in base of the feedback resistance in the diode. And you have studied already in first year, we know the diode equation, that is ID equal to IS e raised to Vd eta into Vt minus 1, and ID nothing but diode current, IS nothing but reverse saturation current, and Vd nothing but voltage of the diode, and this eta nothing but identity factor, Vt nothing but thermal voltage, and e raised to Vd eta into Vt is more than 1. That's why you are not considering 1 here. It becomes I IS e raised to Vd eta into Vt. Then as usual you apply the KCL, that becomes In is equal to Ib plus If. We know Ib is 0 because of input impedance is infinity, and it becomes In is equal to If. And in place of If you can write Id because you are using a diode in the feedback path. I nothing but Vi minus Va by Ri, and here Vi is 0 because of the virtual ground. ID as it is, and Vi by Ri, and we know the ID value Is e raised to Vd into eta into Vt, and Vd nothing but Va minus V naught. Here also Va is 0 because of virtual ground concept, and Vd is equal to minus V naught. Then Vi by Ri as it is. In place of this Vd you can write minus V naught, Is into e raised to minus V naught by eta into Vt. Then you take Is in this side, Vi by Ri into Is equal to e raised to minus V naught eta into Vt. Then take log on both sides, log of Vi by Ri Is into log of e raised to minus V naught into eta into Vt. As usual, this is as it is, and here important thing, log m into n nothing but n log n log m raised to n nothing but n log m. And here the important this will multiply here, and log e raised to e is 1, it becomes minus V naught by eta into Vt, and here log Vi Ri as it is, and this minus V naught by eta into Vt as it is, and we want this V naught, it means this will multiply here, that becomes V naught equal to eta into Vt log Vi by Ris, especially this Ris, eta and Vt, they are constant. That's why the output voltage is proportional to the log of the input voltage. This is about the very simple derivation for the logarithmic amplifier. Very simple. Only you have to remember this diode equation. Remaining as is very simple. As I said, ID is Is e raised to Vd eta into Vt minus 1. This is about the in simple way of your understanding about the logarithmic amplifier. Now we go for another small one, that is about the anti-logarithmic amplifier. That is about the anti-logarithmic amplifier. We go for the anti-logarithmic amplifier. As I said already, very small change in the logarithmic and anti-logarithmic amplifier. What is that change? Now you have to connect the diode in the input side. The remaining it is as similar to the logarithm. Once again we are using the diode equation here, and now we are going for the anti-logarithmic amplifier. And as usual, what is anti-logarithmic amplifier? Nothing but here it is a type of amplifier. In this amplifier, the output voltage is proportional to the anti-log of the input voltage. Once again repeat, the anti-logarithmic amplifier, it is also nothing but is a type of amplifier. In this amplifier, the output voltage is proportional to the anti-log of the input voltage. Or you can write here, the output voltage is proportional to the anti-log of input voltage. This we can derive this equation, and as usual you draw the first figure. As I said already, very small change in the figure, remaining as it is. You can make it the non-inverting terminal grounded, and you can apply the feedback resistor here. can connect the diode in the input side. We can connect diode in the input side. This is nothing but ID. This is nothing but VD, and this is nothing but ID. This is nothing but IF, and this is nothing but IB. And as usual, this is nothing but VA. This is the VB, and here we are applying the positive VCC and applying the negative VA. Only, as I said, only small change. In your logarithmic amplifier, this diode is in the output side. Now the diode is in the input side, and you are applying the input to the diode. You are applying the input to the diode to the inverting terminal and make it non-inverting terminal grounded, and you are applying the feedback resistors RF, and you are applying the biasing voltage positive VCC and negative VCC or negative VA. And as usual, you are using the diode. Now only said the diode equation can write ID equal to IS into E raised to VD by N beta N VD minus 1, and because of E raised to VD eta into VD is more than 1, we can write ID equal to IS into E raised to VD by eta into VD. And here I said already, ID nothing but diode current, and IS nothing but the reverse saturation current, and VD nothing but voltage across the diode, and eta nothing but electric factor, VD nothing but thermal voltage. This E raised to VD eta into is more than 1, that's why I am considering 1 here. You can consider ID is IS into E raised to VD eta into VD. And same thing once again you can apply the how you have done the apply. You have done so many derivations. It's common step. Apply KCL for the node A. Apply KCL to node A. That becomes here the ID, because in current IN equal to IB plus IF. Here same IB 0 because of Zeta is infinity. And here in place of IN we can write here IN equal to ID. We can write IB 0. We can write ID equal to IF. Only the change in place of IN we can consider ID, because you are not connecting the resistor, you are connecting the diode in the input side. That's why it becomes ID. IF is as it is because you are using a feedback resistor, that is nothing but feedback IF. And as usual, ID nothing but you can write IS e raised to VD eta into VD. You can write IS e raised to VD eta into VD, and here you can write IF nothing but VA minus V0 by RF. You can write VA minus V0 by RF. You can write VA minus V0 by RF, and here you can write VD nothing but VI minus VA. Here you can write VD nothing but VI minus VA, or you can write VD equal to VI, because VA 0, here also VA 0, you can write IS equal to E raised to VI by eta into VD, and this VA 0, that becomes minus V0 by then you take this R at this side, that becomes RF into Is whatever by eta into Vi by eta into Vd equal to minus V naught. Then take log on both sides. That becomes log of argument is Rm into e raised to Vi by eta into Vd equal to log of minus V naught. And here, actually here, the important thing we want to minus the negative side, that becomes log of V naught equal to log of Is. And look here, if you take the log here, Is and Rm are consecutive offset, it becomes Is into Rm. And if you take log here, as usual, log m raised to n, nothing but this n log n, this will multiply here, log e raised to is 1, you can write Vi by n Vt, because R can write log E as it is, and then right here minus 71, so right here minus 7, log equal to minus. Then you can simplify it, we get log V naught equal to minus of Is by Rm. This Vi by n Vt, this is log e raised to is 1. It means here actually we want that remove this log, means that apply the anti-log here. It means you can write take anti-log log on both sides. That becomes log and anti-log cancels. It becomes V naught equal to, these are all constant. Take minus Is by Rm into Nt log of Vi by Nv. This is about the importance about your anti-logarithm pair, especially in the anti-logarithm pair, nothing but you can write about this all term, this Is, Rm and Nvt, they are all constant. You can write here V naught is direct equal to the Nt log of Vi. This is about the importance of your anti-logarithm pair. The only thing is that everything is same as is your logarithm pair. As I said, this in your logarithm pair, the diode is the feedback and the diode is the input side. And as usual, we know the diode current, that ID is Is e raised to Vd eta into Vd minus 1, and because e raised to Vd eta into Vd is more than 1, that's because the ID is Is e raised to Vd and eta into Vd, and apply the KCL, In is equal to Ib plus If, Ib is 0 because of that I is infinity, and In is nothing but Id because we are connecting the diode in the input side. Id is equal to If and ID nothing but IS e raised to VD eta into VD, and equal to, we can write IF nothing but VA minus V naught by RF, and here VA is 0, and how we can write VD? The voltage at diode, that is VI minus VA. Here also VA is 0, we can write VD is equal to EI, and here also VA is 0, we can write IS into VI by eta into VD is equal to minus V naught by RF, and if you want to take RF this side, RF into IS equal to ET is to VI eta into VD is equal to minus V naught. Then you take log on both sides, log here, log RF IS into RF T is to VI. I can write here, there confusion means not right here, and write after all I can write here IS into RF. Then you take log minus V naught, log minus V naught, then you take this side, log V naught, this minus go that side, IS and RF, and if you get a set, this is constant, you take outside, log of m raised to n nothing but n log n, this will multiply here, and log e to the AC is nothing but 1, that becomes IS RF as it is, VI by n beta as it is, and actually you want to remove this log term here, that's why you can apply the anti-log here, and we take anti-log on both sides, that becomes log and anti-log, they will cancel, because V naught is equal to minus RF is constant, that is anti-log of VI by n into V, n eta into VT, and actually this IF, RF, n, VT, they are constant, that's the right, the output voltage is proportional to the anti-log of the input voltage. This is about the simple derivation about your anti-log amplifier and log amplifier. As I said, you are completed nearly about 8 derivations. In this 8 derivation, they will ask any one question on 5 marks. And important thing, they are all very simple. It may be inverting amplifier, non-inverting amplifier, adder, subtract. They are very simple. But as compared to the your inverting, non-inverting, and adder, subtract, small difficulty from the your difference integrated, and more difficulties about your logarithmic and anti-logarithmic, because you have to remember the diode equation, because in the logarithmic anti-logarithm you are using the diodes, it may be the input side, it may be the output side, you are using diodes, and you have to remember the diode equation, then it is remaining is as similar to your remaining derivation. Only you have to remember the diode equation, and important thing, as we know, the diode is so important device in electronics. The diode is a two-terminal semiconductor device, it conducts only one direction, and it conducts only power bias. This much having already idea, and you have to remember the diode equation, that is ID is equal to IS e raised to VD eta into VD. ID nothing but diode current, IS nothing but reverse saturation current, VD nothing but voltage across diode, eta nothing but kinetic factor, VT nothing but thermal voltage, and this e raised to VD eta into VD is more than 1. Is so high value as compared to 1, that is why I neglect the 1 here, ID, eta, IS, e raised to VD, eta into VT, and remaining is very simple as how you are done in your adder, subtractor, integrated differentiator. Only thing we know about the diode equation. Thank you. In the next class we go for the remaining things. Thank you once again.